Okay, can you see the file?
Yes, uncle.
Okay. So remember the velocity can be of a wave can be calculated by the frequency multiplied by the wavelength. You're okay with that,
Yes,
right?
yes,
Because that should be a general idea, not only for the speed of the light, electromagnetic wave or sound wave or any water wave or any wave. It is simply velocity is the distance traveled per unit distance. Unit time. So that
yes,
means in a 1 second, how many meters it is traveling or how much length it is traveling. That is the idea about the velocity itself definition or the
yes.
speed, which is the magnitude of that. And when it comes to waves, the length traveled in one period of time is a wavelength, right?
Okay.
And then the
Yes.
frequency itself is how many waves are there in 1 second. Frequency is
Okay.
how many cycles or how many waves are there or how many wavelengths are there in 1 second. So that is why we just multiply the frequency with, because frequency itself will become a 1 over capital T, the period of the time
Yes.
taken for one cycle or one wavelength. Okay. So if you know the time taken for one wavelength and 1 over that, or if you know that lambda is the length traveled in one period and capital T is the time taken for that lambda length travel, then lambda over capital T will be our velocity. Do you catch that? That is straightforward.
Yes. Yes.
And then we know that 1 over capital T, that means capital T is the time taken for one cycle. Then in 1 second, we divide both sides by capital T. That will become 1 over capital T number of cycles in 1 second. So that makes the velocity. General formula for the waves is frequency multiplied by the wavelength. Okay.
Yes.
Okay. And we know that when it comes to light, uh, some other medium, then the refractive index has to be used. Remember that?
Yes. Yeah. Yes.
Because speed of the light in vacuum is the 3 into 10 to the power of 8 meter per second. The refractive index of a vacuum is a 1. That's why the wavelength need not to be changed to the different wavelength in the medium. But the same light travel from one medium to the another medium, it will feel a different refractive index, definitely more than the n equal to 1, which is the lowest value for the refractive index that is in vacuum. So the wavelength, uh, the wave is like, think like we are walking. We are walking with one step size, a wavelength step size. And then let's say we are walking in air. We find it quite okay. But when you get into something like a water or muddy area or something like that, our step size will get shorter. Do you get that?
Yes, uncle.
Okay, so that is what is happening. So how many steps we make per second will be still the same for the wave. That is the frequency.
Okay. Yes.
Frequency in all the medium. So if you have one particular colored light or particular wave traveling, electromagnetic wave traveling from one medium to the other, frequency will remain the same. That means how many cycles or how many steps, how many waves are there in 1 second is going to be the same. But the length, distance covered for every step will change depending on what is its refractive index. Okay. So when you see that the lambda wavelength in the vacuum will be divided by the refractive index. So do you get that? So the
Yes,
wavelength
uncle.
will change. Wavelength will change. Step size will change. And the new step size, whatever the medium step size, will be the vacuum step size or vacuum wavelength divided by the refractive index. So when we include that also in the equation for the velocity, so the velocity will be also get reduced. Okay. It won't be C equal to 3 into 10 to the power of 8 meter per second is the maximum speed that can happen only in the vacuum. Any other medium, the value will be lower. So that turns out to be the velocity in the vacuum divided by velocity in the medium will be our refractive index. Is it okay? So we
Yes, uncle.
need to keep making that connection and everything. And then the refractive index appear here. The refractive index in the medium is given by lambda by n. You're okay with that? So that is the one I was explaining. Okay. And all these things, can you see that here? Like,
Yes, uncle.
okay, all these things. And And even sometime what happens, if you see the wavelength, look at here, there is a particular wave which has a particular wavelength in vacuum, but when it gets into water, which has a refractive index of 1.33, then a 380 nanometer, which is supposed to be a violet color, divided by 1.333, that is the water refractive index, it becomes 760 nanometer. It will go to 760 nanometer per 1.33, or we can say that the lambda will be become shorter. Do you get that?
Yes, uncle.
Okay, so the 380 is our red, the violet color, and the 760 is our the extreme red color. Okay, so the 380 nanometer in the vacuum, 760 nanometer in the vacuum, they are all respectively red and violet and the red. But when they enter into the violet, which is a 380 nanometer in the water, in the vacuum, if you divide by the refractive index of the water 1.33, it converted into 285. Do you get that? It becomes shorter.
Yes, sir.
Okay, but 285 looks like, okay, it is ultraviolet. No, that is a mistake. We should not, only from the wavelength, we should not decide what color or what electromagnetic wave is that. Is that okay? The frequency is the one will decide that. So if you
Yes,
include the refractive index, then only you will get an idea. So the red color, bright red color, 760 nanometer in the vacuum, when you divide it by the refractive index of the water, which is 1.33, that becomes a 570 nanometer. But the 570 is a bright green color. Do you get that? Do you understand that? You are okay with that?
Yes, yes, uncle. Yes.
But it won't change it into a green color.
Yeah.
But 570 in the vacuum is the green. And if you take the 570 vacuum in the green and divide by 1.33, that will be the corresponding wavelength of the green in water. Is that okay?
Yes, uncle. Yeah.
Okay. And then we have seen you're okay with this three-dimensional waveform, the propagation. Is that okay?
Yes, sir.
Okay. And then we just see that as a wave front. So at every point we can consider that like in parallel. So if you take the source may be very far away, like our sun. And then when it started at the sun, looking from here, it will look like a point. And then it will be spherically expanding and propagating. And then when it traveled so much distance, when we see the light, which is a big sphere, part of the very big sphere, with the center as the sun center, and the distance is from the sun to the earth. Do you get that? Such a big sphere.
Yes, okay.
And if you see the waves coming here, it won't be the area what we are seeing, the whole area of the earth surface, the light will be coming as a parallel beam. Make sense to you?
Yes, sir. Yeah.
Okay, it is even though it is sound like a point source, started as a spherical one, but the sphere area becomes so big because of the distance between the sun and the earth, then we call that as a plane wave, because it all travel from one plane to the next plane. All of them will be traveling in phase. Is that okay?
Yes, sir.
Okay, and then we just say that there could be a reflection, and then okay, refractive index can be understood. This we have already seen. Remember that the denser to the rarer, rarer to the denser, total internal reflection, everything we already looked into. You're okay with that?
Yes, sir.
Okay, and then this also we looked into last time. I think this was around the time I said that diffraction is about bending of the wave around the corner, but there should be a relative the size comparison between the wavelength of the wave and the dimension of the corner. Okay, so if it is a door kind of opening, the door gap and the door size and the corner, everything, they are comparable to the sound wave. That's why the sound wave which is entering into the door, it can bend around the walls, and the person who is standing not straight in the opening of the door, even behind the wall, can hear the sound. but that cannot happen in terms of light. Light will be,
Okay, yeah.
yeah, because the size of the door gap under the edge of the door is so big, so the light will go straight. So that will look like, it will look like there is no diffraction at all. But what Young's did, let's say, bring the size of the slit as close as possible, which is comparable to the wavelength size of the light, then it will start become a slit, and then it will start the diffraction. Do you get that? The picture is explaining that we are bringing the slit door size
closer.
as close as possible, and then that is where he thought that, okay, if we can do it with one hole, one slit hole, if we do two of them together next to each other, then it will diffract two waves. So that is what he did. This is the three-dimensional view of the Young's double slit experiment. He has shined light of two slit. The gap of the slit is comparable to the wavelength, and there are two slit with a separation of a distance. And then what happens? There will be a diffraction happening from both the slit holes, and then when they go after that, there will be an interference happening, because wherever the final screen is, the path difference, the distance between the first hole, if you draw a straight line directly to the screen, and the second hole, draw a straight line directly to the screen, the same point, then we will have two different distances. Are you okay with that? Do you understand that? So, okay, let's see this diagram. This diagram will tell us S1 and S2 are the two slits. And then when we go to the screen, this is a top view of the whole experiment. So from the S1 dot, if you go to as a straight line to any point on the screen, and to the same point on the screen, if you draw another line from the S2 to that point, then we know the two different distances. We have to find the difference between the two. If that difference is going to be exactly in the integer multiple of the lambda, then the waves arrive will be in phase. Can you imagine that? Or you want me to
yes, sir.
Draw the picture?
Yes, uncle.
You got the idea, right?
Yes.
So either it has to have half a wavelength, or twice the half the wavelength, or thrice the half the wavelength. Anything in the multiples of lambda by 2, it is quite okay. Is that okay?
Yes, sir.
Okay, so that is what is written here. Half lambda, 3 by 2 lambda, all those things. So they will, okay, I have to correct. Okay, so it will start with a half lambda, and then it can have another lambda added to that. So wherever they have a lambda, 2 lambda, 3 lambda kind of path difference, exactly one wavelength or two wavelength or three wavelength difference will make the light to arrive in phase from both the point. Do you get that? So that is the picture B. You're okay with that?
Yes, sir.
Okay, but in the case of picture A, they arrive exactly at a difference of lambda by 2, or 3 lambda by 2, or 5 lambda by 2, or 7 lambda by 2. Are you okay with that?
Yes, sir. Yeah.
Okay, so that is what is going to make the light to get constructive interference or completely a destructive interference. That one we have seen last time itself, because the amplitude, when they rise from the zero, both the waves rise from the zero at the same time. And also when they go to the peak, positive peak, they reach the positive peak, and they combine together to make the amplitude to go double the amount. And when they go negative also, they go exactly at the same time and the distance, they will go negative, and it will become a minus 2x. That is the constructive interference idea. But in the destructive interference, the waves, they have exactly 180-degree phase shift. That means when it is going to the positive maximum, the other wave will be going to the negative maximum. Then they cancel each other. So that will become a completely a zero result for that. So it will become a dark fringe. So when we go to the screen, we will see that exactly at the midpoint, the distance, EQ distance from the S1 slit and the S2 slit, where they will arrive in phase. That means there will be a maximum intensity at the very middle. And then if we go both sides of this midpoint on the screen, then after some distance, we will have a minimum intensity because of the destructive interference. And after the minimum, there will be a maximum, and it will keep alternatively going as a minimum, maximum, like that. Do you understand that?
Yes, uncle.
But because of the similar triangle principle, you could see that as we go away and away and away, the gap between the fringes will be changing. Do you get that?
Yes, uncle. Yeah, okay.
So we are going to see that how to calculate that. That will be the one of the thing what we need to do. So we are going to simply use a simple trigonometric picture. So S1 slit and S2 slit are separated by a distance D, and we take a 1 point on the screen, which is on the other side. So we are saying that let's draw a line coming from the S1 to that point and S2 to that point. But now what we are saying, let's split that into, let's draw a line from S1 to the other line with an angle theta, so that it will meet it at right angle triangle. Do you see that?
Yes, uncle.
So the the smaller d, which is the distance between the S1 and S2, become the hypotenuse. And then it will, when we draw that kind of a perpendicular line from S1 to the line which is connecting the S2 to the other end, that will give us the small delta L. That will be the path difference. Are you okay with that? Hello? Hello?
Can you hear me now?
Yeah. Hello.
Yes, uncle.
Yeah, I don't know why it has just went away. Okay. Okay. You're okay with that?
Yes, uncle. I said
diagram and
yes,
why
yes.
we are going for a right angle triangle, because we don't need to worry about the rest of the length traveled from both the slit, because they are going to be exactly equal. So we just made a small geometry here by simply drawing a straight line from S1 to the line which will meet it to the perpendicular angle with the line which is connecting S2 to the point on the screen. Makes sense to you?
Yes, uncle.
Then we will use the simply, we know that the path difference is the delta L, and the gap between the two slit is a capital, lowercase d, and then the angle, let's say the angle is the theta, then we can easily say that the delta L is going to be d sine theta. Okay.
Okay.
And also,
yes,
using the trigonometry, we can easily, under the geometry also, we can easily say that if that is the theta, then if you draw a straight horizontal line for S1, go to the screen, and the line which is going towards the point where we are interested, that will be also theta. With the S2 also, that will be a theta, because the distance between the screen and the slit, that one, under the final screen, that distance is quite big compared to the gap between the two slits. Makes sense to you?
Yes, uncle.
Okay, so that is important, because if you keep it very close, then we won't have this approximation valid. Okay, so now we are saying that when the light hit the screen, it can either have a constructive interference or destructive interference. Now go for the condition, the path length, which is given by lowercase d sine theta, if it is equal to m lambda, if m is 0, 1, 2, 3, 4, even positive, negative. Why positive, negative both are allowed? Because from the midpoint where the bright on the screen, where the bright fringe is formed, the order can be either in the top or bottom. Do you get that? Vertically.
Yes.
Okay. So from that geometry, we say that the m equal to 0 is exactly the midpoint where there will be definitely bright fringe, and then the positive one for the m value will be the one above, the one below will be the negative one. Like that, we will be having order of the fringes. And if you see it in the intensity wise, we can see that all the light will interfere and have the maximum intensity at the midpoint. And if you go up and down, either way, you will form the dark fringe and then bright fringe, dark fringe and the bright fringe, and the intensity will be going down. Okay, can you tell me why the intensity has to go down?
Yes.
Think about it. What actually caused this whole thing? From there, if you understood that property, because that is where you said you made the mistake, right? Like
Yes,
difference between
diffraction.
diffraction and okay, now think along that. Now I hope you have a better understanding of everything, right? Now
Yeah.
together, and then use your thought process, or even you think loud. That means you are talking for whatever you are understanding going on in your mind. I will come to know that how you are thinking and trying to get the explanation why the intensity is going down. Think loud. It could be anything.
Yeah.
Yes, that is the way I can help you, that how the thought process has to go. You get that?
Is it like depending on the wavelength?
What made you to bring the wavelength here? What the wavelength got to do with the intensity?
No, intensity and
Intensity means what? It is just the amplitude square is the intensity,
okay,
right?
yeah, amplitude square is intensity.
Yeah.
Yes.
What that to do with the wavelength?
Okay.
So if you are bringing the wavelength, you need to take a step backward and think what is wavelength means. So let's say you are using a red color light. This pattern will be something like
The
this.
energy of the different colors.
Again,
Or
color mean again you are using all sort of terminology available with the wave. Do you get that? But for any explanation or the evidence or the proof you are bringing as an explanation, you need to think about that also. Because if you make a mistake in doing so, then the definition of that also you don't have a clear idea. Do you get that?
Okay, yes.
Okay, let me explain you and see that how I am thinking and explaining about that. Do you get that?
Okay, yeah.
Because I was never having an idea to explain you why the intensity is going down, because I know that, but only after seeing this picture, I thought that I have to mention about that and ask you that question. The light, okay, go to this experiment. The one in the 3-dimensional. Do you see that the light which is shine on the other side is the equal intensity? Do you get that?
Yes.
And the one hit both the slit also equal intensity. But what is happening because of the slit? Even take only one slit. A uniform intensity is entering. Let's go back to the original idea. The diffraction means when the size of the wavelength was so small compared to the door size, it actually went straight. Do you get that?
Yeah, yes.
So completely in the area, in the volume where there is no door gap, you had zero intensity of the light to begin with. Do you understand?
Yes, sir.
Because the diffraction was not at all happening in that case. Do you get that?
Yes, sir.
Okay, but now let's say you bring it as close as possible in the order of the wavelength. See the third diagram. Do you see that the diffraction started? Do you get that?
Yes, sir.
And don't you think that the diffraction will have an angle? Do you get that? So the light which is going straight is not because of the diffraction. It is a straight transmission that will have the maximum intensity. Do you get that?
Yes, sir.
But the light which is bending, don't you see that as the angle of bend goes higher and higher, and if it goes all the way to the 90 degree, completely it will become dark.
Yes, sir.
You understand the whole idea?
Yes, sir.
So if you draw a straight line of that whole slit, that will be where you have the maximum intensity of the transmitted light itself. But if you go angle anywhere above and below, that is positive angle and negative angle, the light after that straight gap, they are all only because of the diffraction. And the diffraction intensity itself, even with a one hole itself, the amount will be getting lower and lower. And after, depending on the size of the slit, after some angle, it will be completely gone. Do you understand that?
Yes, sir.
Okay, so that is what is happening with the two gaps also. So when the two gaps is making two diffraction intensity, the one in the very middle will be the full light coming from both of them. That's why it has the maximum intensity.
Okay, yeah. Yes,
And
sir.
the next order, fringe above and below, the brighter fringe will have lesser intensity than the middle one, because it is the bending of the light of the diffraction which will have lower intensity compared to the one that is come to the straight one. Do you get it?
Okay. Yes, uncle.
Okay, so that angle become very important. So as the angle keep increasing, our intensity will also go down. Is that okay?
Okay, yes, sir.
Okay. And the width of the fringe also will be also affected because of that. Do you get that? The very center
Yeah,
one
yes.
will have
Yeah.
yeah, that is the same idea. It is just like similar triangle. Do you understand?
Yes, uncle.
Okay. Any questions so far?
No, no.
Okay, so here, okay, let me keep it here and see how you are thinking and solving the problem. Suppose finding a wavelength from an interference pattern. So always think like that. Like when we learn some physics, we need to think from what are all the quantities we are interested or involved in that particular case, and what is the other quantities, mean what are all the quantities we can measure, and what are all the other related quantities that can be calculated from the measured quantities. That is the whole study about physics. You get that?
Yes, sir.
Okay, now we have learned about the light and this property and everything. Coming to all the point, you see, finally we got a simple expression of d sine theta equal to m lambda.
M lambda. Yes, sir.
Okay. In there, we know exactly what each and every one of them are doing the job. The lowercase d is the gap between the two slits from their centers. Is it measurable quantity easily or not?
No.
So you are saying that the gap between the two.
Oh, no, no. That is.
Yeah,
As
that
we
is
go
measurable.
on, it will be harder.
Which one? Which one will be harder?
No, the measuring the intensity of the central maxima will be easier.
That is okay, but how about the small
That
d?
we can measure. Yeah, that we
Yeah,
can
that
measure.
also
Yes,
you can measure.
yes.
And we can measure the gap between the bright fringes and the gap between,
Yes.
and we can also measure what order they are, because by counting itself,
Okay.
we know that it is a 0m or +1 or -1 or +2 or -2. So in the expression we got d sine theta equal to m lambda, even the theta is also possible to measure. Do you get that?
Yes, uncle.
Okay, because we can easily see that when we know that the distance between the slits under the screen, if we know what is the distance, and if we know the gap between the fringes, then we can straight away take a paper and make a right angle triangle, and we know that how to calculate the theta value. Do you get that?
Yes, uncle.
You're okay with that?
Yes, uncle.
So except the lambda, everything else is much easier to measure.
Okay, yeah.
So don't you think that this experiment gives a fantastic idea to measure the wavelength of any light in that medium?
Yeah. Yes, uncle.
Okay, so that's the idea of the even problem. So think even how somebody is making a problem. The problem is not because of they have to test or assess the knowledge of the student. It is mostly about the how they are thinking and how things have happened in the world. Do you get that?
Yes, uncle.
So they are saying that suppose you pass light from a helium neon laser through two slits separated by 0.01 millimeter. And 0.01 millimeter, what kind of instrument they could have used in the very beginning or even now? What is the instrument we can use to measure a 0.01 millimeter?
Vernier. No,
Yeah.
that won't.
Vernier is the
Yeah.
one we can use.
Yes.
And have you ever done optic lever experiment?
Optic lever? No. No.
Okay.
Vernier calipers, yes, I've used. Screw gauge, I've used.
Okay. This is very strange because when I did my 12th standard, one of the experiments were optic lever. Okay, we will discuss that some other time. Is that okay?
Okay.
Anyhow, in this problem, they are given the 0.01 mm, which is actually 10 microns. Do you get that?
Okay. Yes, sir.
It's called microns. You know, the micrometer is called a micron.
Okay.
So if you multiply this with 1000, then we get a 10. It's a 10 micron actually.
Okay.
Find that the third bright line, so 3 is also the m value. On
Yeah.
the screen is formed at an angle 10.95 degrees. So all the things what we discussed are all here related to the incident beam. That means from the central beam. That is what they say, that incident beam. Okay.
Yes, sir.
What is the wavelength of the light? So this should be very straightforward, because we know that lambda is actually given by
d sin theta.
theta,
Yeah.
which is the delta L itself, the path length divided by the order. So plug it in. So when we plug it in, and we have to be careful here, the sine angle, when you use it in degree, then the calculator mode should be in the degree. Okay.
Okay.
Then we are fine. Okay. It's not that we need to convert the degree into a radian. As long as we are careful with the calculator mode, then it is okay. Is it okay?
Yes, sir.
Okay. And we calculate the value as a 633 nanometer. Okay. And when the answer is obtained, always to connect it back and think what is going on. They call it as a discussion or something like that. If you see 633 nanometer, and this whole experiment would have happened in the air, right?
Yes, uncle.
And it is almost refractive index 1. So 633 color is what? 633 nanometer. Do you remember the wavelength band of the colors?
Yes, sir.
It ranges from 700 to actually 400 nanometer is the violet, and nearly the 700 nanometer is the red color.
This will be red, right?
Yeah, it's a bright red actually.
Yeah.
I hope you have not seen the helium-ion laser light output, but have you seen the semiconductor laser, the laser pointer we use, red color?
Laser pointer, yeah.
Yes, that is almost in the same color with the.
Okay.
Okay.
Yes.
Now we can use the idea about the physics knowledge, helium neon laser. Do you see that? There is a laser designed with that. So that means whatever the property of laser physics, which is helping the transition of energy level from the. So do you study the energy level diagram, and the h nu energy is actually equal to h nu, or the Planck's constant multiplied by frequency?
Yes. In chemistry last year, structure of atom.
So now think about it. Now we have a wavelength coming out of a helium molecule, because helium comes as helium atoms, the inert gas. Do you get that?
Yes, uncle.
Now use this answer, lambda answer 633 nanometer. What we can understand about the helium itself, which is giving the laser light. So we studied somewhere in the chemistry last year or something, you were saying that the energy level difference between the upper energy level to the lower energy level will be exactly equal to the h times the frequency of the photon,
h nu, yes,
or the frequency of the photon which is emitted. That is the idea, right?
Yes, uncle.
Okay. Now we know h is a constant, 6.63 into 10 to the power of minus 32, right?
You can use hc by lambda to calculate the energy.
Now you see what we first thought, using this experiment, the difficult job of finding the wavelength itself of a light itself is difficult. That was done using a Young's double slit experiment. Do you get that?
Yes, sir.
Now using this value and the quantum mechanics and the Planck's fantastic the pocket nature of the particle nature of the light, and the how that is attached with the atomic structure and molecular structure and everything, we went all the way to say that what is the energy level difference between the lower energy level to the higher energy level in the helium where the laser action is happening. Do you get that?
Yes, sir.
Okay, that's the beauty of the physics and the way we have to think about it. Is that okay?
Yes, sir.
Okay. So that is what they might be discussing in this part, but that should be done in all the time. Is that okay?
Yes, sir.
Okay. So there is another example. So you want to keep looking into those example, or can we go to what else is there in the wave optics?
That's all, uncle, because diffraction is there, this is there.
Yeah, interference, diffraction, all the
Yeah.
other things we have covered for your
Yeah.
10th standard, I think so. Okay.
Yes, yes, sir.
Okay, can we move on to the other topics or something like that?
Yeah, okay, uncle.
Yeah, and one final comment about here. Okay, we have discussed about this Young's double slit experiment, but let's say in the same experiment, let's say if we have used a white light, okay, what would have happened?
Each of it would have had like it will overlap, like the colors will overlap while forming the.
Yeah, but the middle, very center one will be equal.
Will be white.
Because all of them will have the same
Yeah.
lambda difference, and each lambda is different. You get the, let's say there are 7
Yes,
different
yes.
lambdas. But as you go above and below, what will happen?
Specific colors will be seen.
Yeah, the colors will also get spread.
Yeah. Yeah, yes, uncle. Yes.
The very middle one will be a bright white light because that is a straight transmission, but the other one will have the rainbow colors. Do you get that?
Okay, yes.
Okay, and that can be enhanced by the slits we put. Instead of 2 slits, we can put 3 more than 2. We called that as a grating. You're okay with that? Have you ever
yes,
heard about the gratings?
Grating, yes, uncle. Like, yeah, we did an experiment, yes.
Yeah, so now you see this is what the idea is. Young's double slit experiment
Okay.
is only double slit, but if you put multi slits, then we can get the grating, and that is why in the grating, the very 0th order will be a white color if you pass the white light through the grating, but the first order, upper and lower, and the second order, the intensity will be reduced, and the rainbow colors will be spread out, and the spreading of the color will be, the spacing will be increasing as you go order to the order. Do you get that?
Yes.
Okay, so that's the idea. Okay, so all these things are all fine. So this is the idea about the double slit experiment, and the grating will actually make the fringe very narrow, and there will be multiple interferences happening, and it will have lobes like that. Okay.
Yes.
Okay, we don't need to do all these things for your level, and all these things are okay. And they are explaining that even have you seen the CD? The normal.
Yes. Yeah.
CD.
Yes.
If you see it and different angle, it will show you rainbow color because the CD has
yeah.
layers, and then the light goes and get reflected. They are like filters. Okay, so that is what is happening. Is that okay? Okay, so
yes,
you
sir.
want to continue with any topic in the physics or anything in the maths or something? Which direction you want to go now?
Okay, yeah, can we do like no
Whatever
integration?
Integration, okay.
Yeah.
Okay, even the whole calculus, did we discuss or not?
Yes, we have done it.
Yeah, we have done the calculus. We have started the calculus idea, right? Okay. So
yes.
Let's share here the whiteboard, and then I will take it from there. Okay, where is the document? Okay, can you see the white?
Yes, uncle.
Okay. So the differentiation and integration, long time back, I might have even given you with even deriving the equation for the, you remember how we derived the equation for the accelerated motion? Remember that? Accelerated or decelerated motion, where we say that, first of all, we know that S is a function of time. S is our distance.
Okay, yes, I remember. And then velocity will be.
Yeah, velocity will be given by what? First of all, S is a displacement which has both magnitude and direction, and T is the time, which is a scalar quantity, according to our understanding so far. And now we are saying that whenever something is dependent on other quantity, we are always interested there will be a change happening in the independent quantity from t to t plus dt. And similarly, the dependent quantity itself will change from the current value S to its new value. It's a ds. Okay.
Yes, sir.
So now we are interested in the relative change happening with this these two quantities, that is ds over dt.
That
And
will be V.
yeah, this is what we define that as the V, which is called
Then dV by dt will be A.
yeah, but we need to have that only when the V is also time varying, then we do that. Okay. So
Okay.
that is why. So if the V is also is a time varying quantity, then voila, we ask the next question immediately. It goes as, okay, this means V itself is going to change from its current value plus its small change value. Do you get that?
Yes, sir.
Then that is actually compared with our original T, which has changed from T plus dt. Then we take these two quantities, we just find the relative change happened with the velocity itself with respect to time. This we defined as a.
Okay, yes.
Our acceleration. So we stop here because the gravity and all those kind of acceleration, everything is going to be constant. And that is why in this level, we take it as, okay, A is a constant. Is that okay?
Yes, sir.
How to say that constant in the mathematics? We still try to find, is there any change happen to the A with respect to the time? We would get an answer 0. That is the meaning of constant.
Yes, yes.
Okay?
Yes,
So
sir.
accelerated motion or decelerated motion means A is not equal to 0. Is it okay?
Okay, yes, sir.
But constant. Is it okay?
Yes, sir.
But dA by dt is actually equal to 0. So when that is coming into picture, you see already the calculus is involved in here. Do you get that? Because of the functionality S of t and V of t, that is where we start. We know that dV by dt is actually equal to a constant A. This is where we did our job of, okay, when I know this is a constant, how to recover our V of t. From this whole thing, we are asking the question how to recover V of t. Is it okay? Because V is a time varying quantity, but the change happening to the velocity with respect to time is a constant. Then all we say was, like a V is a variable, something like that, and we consider that go to infinitesimally small value, that is a dV, or call it as a delta V. Is that okay? Very small value. And we put a limit of that delta V goes to 0. Sorry, delta T. Okay, even if you put delta V equal to 0, and we are going to summation of all the delta V's. Do you get that?
Yes, sir.
Okay, so this is what we define as integral of dV. So any variable, if you go to a teeny weeny small size and you make a limit of that size itself going as close as 0, because we don't know where the change is happening, in which order the change is happening. Do you get that?
Yes, sir.
Okay, something may be changing in a very small value, as close as near to the 0. So that's why we define, like, we let that change as close as possible to 0. And if you have that small piece of that quantity, where from one quantity to the other quantity, there is no change happening. Do you get that?
Yes, sir.
So that is why we go to that level, and then we sum all of them, we get the integral dV, we will get back the V itself. Is that okay? So because
Yes,
of
sir.
that, we just say that the dV can be written as A dt. And you remember the mathematics we did. Integral dV is actually equal to integral A dt. And two things we have done here. First is we have taken the A outside because that is a constant. Do you get that?
Yes, sir.
Because A is a constant. And then After that, we did another one also. Let's do that. Integral dv is actually equal to a integral dt. This integration is with respect to the independent variable. Then we want to understand when time t equal to 0, what was the velocity itself? Do you get that? Velocity at time
Yes.
t equal to 0. We initially take the velocity as a u. Okay, so this is called the initial velocity. Initial velocity, because velocity at time t equal to 0. Okay. Initial
sir.
velocity. And we want to know for all the time, in general for all the time, which is nothing but our v of t. We are recovering that. Is that okay? So the limit has to be related. You're okay with that?
Yes, sir.
Either way. So that is why we learned the definite integral also. Now we know that the answer for this integration is a v with a limit of u to v of t, which is equal to a times the t itself with the limit of 0 to t. Okay. So that all fall in place. Then it will be upper limit minus lower limit is equal to a times the upper limit minus lower limit. So this end up to the v of t. The time varying velocity is nothing but the initial constant velocity plus the linearly time varying velocity. Is that okay?
Yes, sir.
So that comes to, in terms of the diagram also, we will say that there is a initial velocity u when t is equal to 0. And after that, it is going to be a straight line. Is that okay?
Okay, yes.
And if you take a 2 point, as it is a straight line, we can take whatever the width we want. If you call, this is the, because this is the velocity, upward direction is the velocity axis and this is the time axis. This is the change happened in the velocity to the change happened in the time. So the slope, the slope or the gradient m is actually equal to dv by dt, which is our acceleration, which should be a constant. That is a constant in the straight line also. Do you get that?
Yes.
So that is how all the quantities are, all are there related. So there is a straight line equation and that one goes over here. So we know that how the integration and also the definite integral and through the inverse process of the differentiation is the integration. Is that okay? So in mathematics,
Yes,
we do a lot of other things to learn about different function, how to integrate. So the very basic thing about the calculus is, let's understand from the differentiation, and every problem you do the differentiation, immediately think about the integration. Because you need to get back the answer. Let's say
Yes.
you take a function. In math, always we take the function as a x, which is actually defined as, let's say it is a x itself. You're okay with that?
Okay, yes.
Okay. So now, even though we say that this is actually y of x, it's a function. Is it okay? So in
Okay,
this, we say that x is the independent variable, which is changing from x to x plus dx, and y is changing from y to y plus dy. Then we take the relative change happened between these two, that is dy by dx is our interest. Do you get that? So the forward process of calculus is differentiation, which we are interested in. Change happened to an dependent variable with respect to the change happened in the independent variable. Okay. So when you ask for dy by dx, immediately we need to know that it is nothing but differentiation of differential operator with respect to x acting on the function y. Okay, always remember that. Is that okay?
Yes, sir.
So we can plug in the whatever the definition given in that problem for the y, that will tell, okay, dx is a small change happened in the x, numerator, denominator, same quantity can be factorized 1 to 1. The answer is 1. Is that okay?
Yes.
Okay. So let's say if this is a first example. Let's say the y is actually going to be a 3x. Then also we can do the same thing. If you are interested by dy by dx, then it is going to be d by dx of whatever the 3x. Step back and then try to get the help rather than taking the 3 out. What is the meaning of 3x itself? In general, 3x means what? Basic mathematical operation.
Yeah.
This, what is the mathematical operation happening between
Oh,
the
multiplication.
multiplication? What is the
Yeah.
basic definition of multiplication?
Repeated addition. So it's x plus x plus.
So x plus x plus x. You're okay with that?
Yes, sir.
That is what is helping us to get the differentiation done. Do you get that?
Okay. Yeah.
So now, with respect to the x point of view, which is we are differentiating with, all the quantity which are getting added with, all of them are, there is addition going on. Do you get that? All of them
Yes,
are
sir.
dependent, doesn't matter. So then what we do, it is like just d by dx. It is like multiplying to each and every term. Do you get that?
Yes, sir.
So that will be dx by dx plus dx by dx plus dx by dx. Okay. So each of them will be factorized to 1 to 1. And that will end up with answer as a 3. Is that okay? You're okay with that?
Yes, sir. Yes.
Okay. So now we got an answer. Dy by dx is actually equal to 3. Let's say this is the starting point. Like our acceleration with respect to time is a constant value, means it may come as an answer as a 3 meter per second square. Do you get the analogy with the physics?
Yes, sir.
Okay. So now let's say we want to recover the y itself. Y is equal to what? Then what we need to do? We know that a simple dy will give us the y itself. So all we are going to say that is dy is divided by the dx, multiply dx on both the sides. Is that okay? Very basic stuff. Is that okay? So that
Yes,
we
sir.
can factorize 1 to 1, then dy will be equal to 3 dx. Voila. Now we integrate. Then we know that with respect to x, this is actually a constant, or we can say that this is nothing but what is 3 dx? Is a dx plus dx plus dx. Is that okay? Same principle.
Yes.
Okay.
Yes.
That makes us integral dy. In this case is a integral dx plus integral dx plus integral dx. Okay, so we say that y is nothing but x plus x, which is a 3x. We recovered that. Is that okay? Because we started with y equal to 3x, differentiated yield dy by dx equal to 3, and we integrated the dy by dx with respect to x. That yielded back our function itself, which is y is actually equal to 3x. Is that okay? You see how the mathematics is working beautifully.
Yes, sir.
Okay. So now if you have y equal to 3x plus 2, we would have done the same thing, but the differentiation itself would have lost the 2. Okay.
Yeah.
Okay, that is the reason when you integrate finally, you got an answer. The dy is actually got an answer as a 3x. We need to add a integration constant. It is a must. Okay.
Yes, sir.
Integration constant. So now, sometime they may give some limit integral. So let's say we know that the original function was y equal to 3x plus 2. So what is the condition? X equal to, initial condition is when x equal to 0, the y is actually, y of 0 is 3 times 0 plus 2. Is it okay? Hello?
Yes, sir.
Okay. So they may
Yes.
give this initial condition. Y of 0 is actually equal to 2 or something. So once we found the final answer is y equal to 3x plus c,
3x.
we can make use of this to get a recovery of the c value. That is 2 is actually equal to 3 times 0 multiplied by c, which gives c equal to 2. This is one way to recover the integration constant. Okay.
Yes, sir.
Other way to recover is when we are integrating the dy is actually equal to 3 integral dx. We would have the initial condition as when x equal to 0, y is actually equal to a 2. And when x is equal to, for example, 1, y is actually equal to a, how much value it should be? 5. Okay with that?
Yes, sir.
Okay. So that will also, when you put the limit, so normally in the mathematics, they would just simply write it as find dy, integrate and limit 2 to 1. 2 to 5. That is what they will give. Do you get that? So this will be integrate completely and then put the limit 2 and 5. So the answer is here 5 minus 2 is equal to 3. Are you okay with that?
Yes, sir.
So, but actually this is what is going on. So we know that this side will completely will become a 3 or that is okay, but that is for the particular case. But let's say we just yeah, okay. So this side is going to be okay. How to apply that? Okay, now I would okay. I would change it to x equal to x and y equal to y.
Oh.
X is y itself, y is a y of x. You're okay with that? Because that is what the
Yes,
actual meaning is. Do you get that? So this one will
Yes.
become a y of x minus 2 will be equal to 3 into x minus 0. Okay, so the y of x will be equal to 3x plus 2. Okay.
Yes, sir.
Okay, do you have another tuition or something appointment now, or you have few more minutes?
I have an other class.
Okay, then we continue next week. Okay, I
Yeah.
want to get
Okay.
into the product rule and the chain rule, and then how we can use that for the integration also. That will be a
Okay.
better way rather than I go directly to the integration like integration by parts or substitution. Okay.
Okay. Yes, sir.
Okay, Karishma. See you next week then. Take
Yes.
care.
Thank you.
Okay, bye.